Hi everyone, welcome to my calculus calculus 3 class channel on YouTube. This is probably the first video that you should watch for one big reason. It's because this is where the course starts, right? It's the basis that you have seen in Calculus 2 on which we will build on. But unfortunately, we don't really have the class time to review it. So that's why I'm making it as a series of short videos. This is the first video. In the first video, we're not going to do much. We're just going to lay down what's a power series and what are the ratio and root tests to figure out when the power series converges or diverges. So, okay, what is a power series? It has two main forms. The most general form is this one over here. So this one is general when it's centered at x equals a. A could be any number, right? It could be like 0, but it could also be 1, 2, pi, whatever. Then the series is written like this. You have x minus a here, and it's basically a polynomial of infinitely many terms, uh, of infinite degree as well. So you have like x minus a squared. Then if you were to continue, you would have x minus a cubed, x minus a to the power of 4, and this goes on forever. Now, it's interesting to look at the specific form when x is equal to 0. So in that case, the power series is expressed in a much simpler way, because instead of having x minus a every time, you just have x, right? So you have an x term, x squared, x cubed, and so on. It's generally a bad idea to expand something like this to make it look like something like that. Because when we write a power series centered at a, it's because we have a good reason to do so. Otherwise, we would be writing something like this, which is much simpler. Down. Notice that these series have a variable x. Most of the times in calculus 2, when you saw series, they were numerical series. Like they were just sums of numbers that could either converge or diverge. Well, this is still the case here, but it depends on the value of x. So for each value of x that you choose to substitute in here, the series you will get is a numerical series that could either converge or diverge. So now the question becomes, for which values of x are these series convergent, and for which values of x are they divergent? And to answer that question, we're going to use two main tests. The ratio test first. So suppose that we replace a value of x, okay? And we get a numerical series like this. And then we make L, which is the limit at infinity of this, right? An plus 1 over an. So in other words, we divide two successive terms, and we leave n undetermined, and then we take the limit as n is approaching infinity. Then if that limit is lower than 1, the series is absolutely convergent, okay? We won't focus too much on the word absolutely. I invite you to review it in your Calculus 2 notes. You should know about this. But convergent is what's important here. Now, if L is greater than 1, the series diverges. Now, I want to point out that it's possible that this limit exists. It's possible that this limit doesn't exist. And it's also possible that this limit is infinite. Okay? So if the limit is infinite, you are in this case, the series diverges. Okay? Now, if L is equal to 1, or if the limit simply just doesn't exist, then you cannot conclude anything. Okay? So then the ratio test is inconclusive. And we will see what we will have to do when we get to that conclusion. Now there's another test. I call this the younger sister of the ratio test. It's called the root test, which has the same premise, the same theorem, let's say, but instead of calculating this limit, we calculate another limit. So now let me erase this in order for me to write the root test. So root test, okay? So you will see it's very, very similar. Consider the series an, and L is equal to the limit as n is approaching infinity of the nth root of the absolute value of an. Then, okay, number one, if L is smaller than 1, the series is absolutely convergent. Thus convergent. Okay, I'm not going to say the full word here. Number two, if L is greater than 1, but keep in mind this includes the infinity case. If you have the limit to be infinity, it also works. It diverges. Now, if L is exactly equal to 1, but this also includes the case in which the limit simply does not exist. So the ratio test is inconclusive. Okay, so why do I call these theorems brothers and sisters? They say essentially the same thing. The only difference is in how you calculate the limit. Notice that I wrote the exact same words. The only thing that changes from one theorem to another is the limit that we compute to get to the desired conclusion. So, all right. I'm just going to underline everything so that you can see that this is indeed what we have. So when L is greater than 1, it diverges. And if L is exactly equal to 1, then ratio test is inconclusive. Now, I want to remind you that this is also the case when the limit does not exist and is not infinite. And same thing here, right? Or limit does not exist and is not infinite. Whereas in these cases, the limit not only is greater than 1, could end up being infinity. So, or infinite limit. It cannot go to negative infinity because you're using an absolute value, right? All right, that's what I wanted to present for this first video. So in the next video, in the next two videos actually, we're gonna see two examples. We're gonna see a couple of examples actually in the next couple of videos. Here we go.